here we have binding energy and binding energy per nucleon. Okay, what's the difference between binding energy and binding energy per nucleon? So we know that binding energy, the symbol is EB. Okay, EB. But for binding energy per nucleon, it is EB divided by the nucleon number or the mass number. Okay, so first of all, let us look back to binding energy. Binding energy is the energy required. Okay, required to you need to supply this amount of energy. Supply this amount of energy in order to be absorbed by the nucleus. So to separate the nucleus into the individual protons and neutrons, these protons and neutrons are the nucleons. Okay, it's to separate the nucleus. Okay, it's separate what? Separate a whole nucleus. Separate a whole nucleus. That means binding energy is actually we can say it is like we have a nucleus. Okay. Nucleus, it has protons and neutrons. Okay, you have protons, neutrons all over. Okay, separate the whole nucleus. Okay, separate the whole nucleus into all the individual proton and neutron. All right, you have proton, neutron. Okay, separate the whole nucleus into individual proton and neutron. Whereas binding energy per nucleon is actually the binding energy per nucleon is the energy needed to remove one nucleon only. Remove one nucleon is this nucleon can be proton or neutron from the nucleus. Just to remove one nucleon, proton or neutron from the nucleus is like I have the same nucleus here. I have the same nucleus here. Okay, the nucleus. So binding energy per nucleon means I remove just one. I remove maybe just draw another one, and then just to remove maybe just remove one of it. Remove one of it out. Remove it. You see that? Okay. Just to remove maybe one neutron. One neutron, or it can be a neutron or can be a proton. Okay, can be a neutron, can be a proton. So here for just now for this one, to separate a whole nucleus into separate the whole thing into proton and neutron, this one will require binding energy EB. But if you just want to separate only one particle from the nucleus, separate either one, you take out one neutron, or take out, yeah, you can say take out one neutron, or you take out one proton. Okay, take out one neutron or take out one proton. These neutron and proton, they are all nucleons. Okay, you take out one neutron or take out one proton from the nucleus. Okay, I just want to say, okay, this one you require binding energy per nucleon. Okay, just to remove only one particle from the nucleus. This one is binding energy per nucleon. Okay, so how to get this binding energy per nucleon? We just take the binding energy we calculated from delta mc square just now. We divide by the mass number, or divide by the nucleon number. So what is A? A is called the mass number, okay, or the nucleon number. Do you see that? This is the formula. Binding energy per nucleon is the binding energy we calculated just now, which is delta mc square. Okay, delta mc square. Divide by the nucleon number. A is the nucleon number, which is the proton plus neutron. Or we can say this is the mass. Maybe just make it red color. This is the mass number. A is the mass number. Okay. The binding energy divided by the nucleon number or mass number, we get the binding energy per nucleon. Okay, proton plus neutron. which is the A. Okay, so you see this A is the mass number. Yeah, we already explained just now. In the earlier part, A is the on top here, the mass number or nucleon number. This is the A. Okay, Z is the proton number or atomic number. Don't say that A is the atomic number. A is not atomic number. A is the mass number. Z is the atomic number. Atomic number is the proton number only. Okay, don't confuse. Don't confuse with the alphabet. Yeah? A is atomic. Wrong. A is the mass number or the nucleon number. So for example, like let's say I have I just take one example. Let's say I have the carbon 12 again. Carbon 12. Okay. So how to find the binding energy per nucleon? Binding energy per nucleon. Just calculate your binding energy first using the formula delta mc square. Okay, divide by the nucleon number. You take the one at the top here. Yeah, divide by 12. Divide by 12. Not divide by 6. Divide by 12. This 12 means the proton plus neutron. You understand? The proton plus neutron. Why? Maybe you ask me why we need to divide by the nucleon number. Later I will explain why. Yeah. Okay. So divide by 12. Divide by the mass number. Yeah. Nucleon number is the mass number. Okay. So understand the difference between binding energy and binding energy per nucleon. Binding energy is to separate the whole nucleus, but the binding energy per nucleon is to take out just one nucleon, take out one neutron, or take out one proton. The binding energy per nucleon for neutron or proton, take out one neutron or take out one proton is the same. Although we know that neutron has a neutral charge, proton has positive charge, but the energy required to remove one neutron or energy required to remove one proton, they are equal. They're same. Okay, they are the same. Okay, so neutron and proton, to remove one of it, they have equal energy. Yeah, equal energy. We don't look at the sign at all. Okay. Yeah. So binding energy, to calculate the binding energy, you just use delta mc square. But binding energy per nucleon, after you get the binding energy, you need to divide by the nucleon number. Divide by the nucleon number or mass number. Then only you get binding energy per nucleon. Okay. So now let's go deeper into binding energy is the energy required to separate a whole nucleus. Binding energy per nucleon is energy required to supply to take out just one particle or take out one nucleon from the nucleus. Okay, just remove one particle only. Okay. Binding energy is to separate the whole thing. Okay, now binding energy per nucleon is the mean or average binding energy of a nucleus. Why we say average? Because we divide by the nucleon number. That's why we say average. Average binding energy for a nucleus. Okay, it has a special name called average. The binding energy itself is not average. Binding energy per nucleon is the average binding energy inside the nucleus. This is important. It is a measure of nuclear stability. Why we need to divide by nucleon number? Why we need to divide by nucleon number? It is because we want to talk about nuclear stability. How stable is the nucleus? Can the nucleus decay? Is it radioactive? Is it stable, or will it change to other form of nucleus? All this is regarded about binding energy per nucleon. Okay, so it is a measure of nuclear stability. So binding energy per nucleon is proportional to the nuclear stability. Okay, it's not just binding energy, but nuclear stability depends on binding energy per nucleon. Okay, we can say this binding energy per nucleon, it is proportional to stability of nucleus. Okay. Maybe we can say like that. This one is proportional to the. Okay, let me write again. It is proportional to the stability of nucleus. Maybe I should just use other color. Just use green. Yeah, stability of nucleus. So, how to know whether okay. Now, okay, talking about stability of a nucleus, it is proportional. Stability of nucleus is proportional to binding energy per nucleon. Why do we say like that? First of all, we can say the higher the binding energy, the higher the binding energy, the more stable the nucleus. Why we say like that? Why do we say like that? You see, what is binding energy? Again, what is binding energy? Binding energy is the energy required to supply, isn't it? You need to supply. This amount of energy. You need to supply the energy equivalent to the binding energy in order to be absorbed. In order to separate the nucleus. So if the binding energy is high, that means you need to supply more energy. You need to supply more energy required to be absorbed. You need to supply more energy. So if you need to supply, all this go back to the earliest part. When it combine, let's say when it combine, it release a lot of energy. Let's say it lost, or we can say a lot of mass defect. The mass defect is high. Let's say the mass defect is high. Okay. Let's say the mass defect is high. So when the mass defect is high, then there will be a lot of energy release. This energy release becomes the binding energy. So when a lot of mass defect, as this happens especially for the big nucleus. When a lot of mass defect, a lot of energy release, then there'll be a lot of binding energy required. So when a lot of mass defect, a lot of energy release, and a lot of binding energy required, so next time you want to separate this nucleus back to proton and neutron will be harder, because you need to supply more energy to be absorbed. If initially when it combine a lot of mass defect, a lot of missing mass, a lot of energy is released, so that means it has very high binding energy. So next time you need to supply a lot of energy in order to be absorbed by the nucleus and to separate the nucleus back to mass of proton and neutron. Understand? So if you need to supply a lot of energy to overcome the binding energy, supply a lot of energy to be absorbed, means the nucleus is very stable, because it's hard. Because if you need to supply a lot of energy, this means that it is hard to separate the nucleus. If you need to supply a lot of energy, means it's hard to separate the nucleus. Hard to separate the nucleus means the nucleus is very stable. Nucleus is very stable. Okay, make it like this. Let's say the mass defect. Okay, I summarize like that. If the mass defect means loss a lot mass. Okay, release. If the energy release is high, this energy release becomes the binding energy. Becomes the binding energy. Okay, becomes if the mass defect is high, release a lot of energy, the binding energy is high. So that means this energy is also the energy need to supply. So if last time you release a lot of energy, so it has a very high binding energy. So next time you need to supply a lot of energy. If you need to supply a lot of energy, means it is hard. What I can say is, if you need to supply a lot of energy, means it's hard to separate the nucleus back to proton and neutron. Hard to separate the nucleus. This means that the nucleus very stable. The stability is very high. Okay, so a lot of mass defect means the nucleus very stable. We straight away look from here. Mass defect relate to the stability. This is the stability. So a lot of mass defect is good for the nucleus. If the nucleus has a lot of mass defect, means the nucleus is very stable. Yeah, because you need to supply a lot of energy in order to overcome the binding energy, or we need to supply a lot of energy in order to be absorbed by the nucleus to form back the perfect proton and neutron. Yeah, if you need to supply a lot of energy, just to separate the nucleus, this means the nucleus is very hard to separate. Very hard to separate the nucleus means the nucleus is very stable. Okay, you get the common sense, the logic. That's good. Okay, let's go back. So in short, what I can say is, the higher the mass defect, the higher the binding energy. Okay, the higher the mass defect, the higher the binding energy. So the higher the mass defect, the higher the binding energy. The higher the binding energy means the more stable the nucleus. Okay, more stable nucleus. This normally, if we talk, just say about carbon 12, it will that means it's a 6 proton plus 6 neutron. You get a carbon nucleus, isn't it? Maybe this one the mass defect is just 0.5 gram. Okay, but if you're talking about uranium, let's talk about uranium. I'm not so sure what is the proton number. I think it's around 80. I'm not so sure. Assumption 82. Okay, so this one will have 82 proton plus how many neutron is there? Let me calculate. 238 minus 82. So how many proton? There are 156 neutron. Okay, for this case, okay, like just now you're talking about the carbon 12. The mass defect maybe is just 0.5 gram. But for uranium, if you use so many proton and so many neutron, the mass defect will be even higher, greater. The mass defect will be a lot. Maybe this one will go up to maybe 10 gram. Yeah, compared to this one, 10 gram. This one just 0.5 gram. This one 10 gram. So that means this one uranium, it has higher binding energy compared to carbon. Yeah, because the mass defect is even higher. Do you see that? This one lower mass defect, this one higher mass defect. That means this one the binding energy is lower. This one binding energy definitely bigger. Because we use the formula what? Binding energy equal to delta mc square. We can say the higher the mass defect, the higher the binding energy. So supposed to be uranium has higher binding energy because it has a lot of mass defect. You know, for big nucleus, the bigger the nucleus, the more the mass defect. Yeah, the more the mass defect. And the more the mass defect for bigger nucleus, then there will be more binding energy. But this is just one-sided view. Yeah, if you just consider about the binding energy only to relate with the stability, this is only one-sided view. Yeah, we cannot relate stability with only binding energy. We need also to regard the nucleon number. Stability is not just affected by binding energy, it also affected by nucleon number. Why do I say like that? Because it is because of the protons inside the nucleus. We know that proton and proton, they repel each other, isn't it? Proton and proton, they repel each other, especially when they are very close to each other, because they have same sign. Same sign, they repel. This is we learn about electrostatic. We learn about Coulomb's force. Coulomb's force. And the force, Coulomb force is what? KQ1 Q2 over R squared, our first chapter, isn't it? Our first chapter. So, and we know that if there are more proton together, there are even greater force. Greater force repel them from each other. And we know that the nearer, so if the R, the distance, smaller, there'll be even greater force. Greater repulsive force if the protons are very close to each other. This especially happen in the uranium. Uranium, although we say that it has very high binding energy, supposed to be the stability also higher compared to the carbon 12, isn't it? Because this uranium has higher binding energy, it's a big nucleus, the mass defect must be even greater, so stability must be even greater, supposed to be for uranium. But in terms of nucleon number, if we compare the nucleon number, carbon is just 12, but uranium is 238. So for nucleon number, okay, the relationship between nucleon number and stability is, okay, let me rub this off. The relationship between nucleon number and stability is, the higher the nucleon number, the lower the stability. It is inversely proportional. For binding energy with stability is directly proportional, but nucleon number and stability, it is inversely proportional. The higher the nucleon number, the lower the stability. Because if for carbon, it is just 6 proton. 6 proton, 6 proton is just how many proton repel each other? 6 proton is just 6 proton, only 6 proton are there, repel each other. But for uranium, it has 82 protons, very close, tightly packed in the nucleus. I cannot draw all protons here. There are also neutron here, but there are 82 proton here. Even greater force repel each other. So anytime they try to split themselves, you know that this Coulomb force act against the binding energy. It act against the stability. It lower the stability. Why I can say the Coulomb force lower the stability. So although it has very high, uranium has very high binding energy, but the nucleon number is very high also. The nucleon number, we say the 238. The nucleon number 238 is also very high. When nucleon number is very high, means it has a lot of protons. It has a lot of protons. A lot of protons means the Coulomb force, the electrostatic force also very high. When there are a lot of repulsive force in the nucleus, so it lower the stability. Then the stability become lower. Understand that? So in short, what I can say is talking about stability of nucleus, stability of nucleus is proportional to binding energy per nucleon. So the higher the binding energy, the higher the stability. However, the higher the nucleon number, the lower the stability. Okay. So this is that's why we cannot just take binding energy. We cannot just consider binding energy for the stability of nucleus. We need to consider also about the nucleon number. That's why when we talk about stability of nucleus, we use binding energy divided by the nucleon number. Okay, I think that's all for the lesson for this video. Okay, let's move on to the next one.